Hi everybody, Augie Kennedy back here with super awesome calculus. Well, we're on the home stretch now. We're on chapter 6, which will be the last chapter we cover, entitled Integral Applications of Integrals. So basically, last time we went over the idea of what an integral was. We talked about the fundamental theorem of calculus, and we explored how to solve integrals. Here in this chapter, we're going to go over various ways to find integrals. We're going to look at areas between curves, how to find the volumes of solids of revolution, which I'll explain, and the average values of functions. Now, this will be a lot more computational than most of the other lectures. But don't be intimidated by the geometry. The geometry that we'll be covering here is actually very, very simple. So you shouldn't have too much trouble. Now, today we're going to look at how to find the areas between curves. Okay? Now, for instance, what we're going to be looking at is, let's say we've got your coordinate plane here. Let's look at x squared, the positive side of x squared, and y equals x. What if we want to find out what the area of that little sliver is in there? Well, it's actually not that hard to figure out. This can be solved, the area between, if we want to solve from b to a, first thing we need to do is we need to identify which function is on top. In this case, between a and b, if this is y equals x and this is y equals x squared is on top between a and b. However, if we're looking between b and c, y squared is on top. So, find out which function is on top first, and then we're going to subtract that by the function on the bottom, and we're going to take the integral of that difference. This is actually pretty easy. You write it, in general, like this. Between a and b, the area of that curve, the area of the space between those curves, is the absolute value of f of x minus g of x, wherein you'll have most of the time, the absolute value takes care of negatives, but you want to make sure you have the top function being the upper one. So let's take a look at how this works. Let's look at a nice example here in the book. All right. This is a pretty good example. All right. So we want to find the area of the region enclosed by these two parabolas. Y equals x squared. We know what that looks like. And y equals 2x minus x squared. We can very easily plot some points and figure out what that looks like. Oh, I'll save you the time and the trouble. We're looking at this. Oh, and we want to find them between the points of intersection. So the first thing we do is we graph them. You'll want to plot points if you can. But we know y equals x squared, but we don't really know 2x minus x squared. We have an idea that it's going to be an upside down parabola type thing. So the first thing we need to do is find out where these points intersect. Where do these curves intersect? Well, this is pretty easy to do. All you need to do is think about what intersection means. Intersection means the value, the y, is going to be equal in both. For them to intersect, if this is 2 and this is 2, there will be an intersection. So in general, we want to set these two functions equal to each other. We get x squared equals 2x minus x squared, which turns into 2x squared minus 2x equals 0. So 2x minus 1 equals 0. So we're going to have intersection at x equals 0 and x equals 1. which makes sense. So plugging in the y value, we could plug 1 into this function, and we'd get 2 minus 1 is 1. 1 squared is 1. 0 squared is 0. 0 minus 0 is 0. So it holds. So actually, if you were to plot this out, you'd find that we'd have intersection here at 0. And here's 1. There's 1. And we'd have an intersection here at 1. So you can see that this is the area right in there, this little area. That's what we're going to want to be finding the area of. But this is pretty easy. This is pretty easy because we can see that we have y equals x squared on top, on the bottom, but in this shaded area, the function that's on top, right up here, is y equals 2x minus x squared. So we're going to be looking between the points of intersection, 0 and 1, of the integral of the top minus the bottom. Let's check it out. So we want the integral from 0 to 1 of 2x minus 2x squared. The top minus the bottom. 2x minus x squared minus x squared is 2x minus 2x squared dx. And this is a very easy integral to solve because, well, first of all, we can take out the 2 between 0 and 1 to get x minus x squared dx, which makes it even easier because then we're just looking at x squared over 2 minus x cubed over 3 between 0 and 1. We know that 0 is going to eat the bottom. When we plug 0 in, we're going to get 0 over 2 minus 0 over 3. So really, the 0 doesn't matter. The only thing that's going to matter is the function evaluated at 1, which is going to be a half minus a third times 2. The 2 is going to cancel out the half. And we're taking the absolute value, remember, so we get 1/3. And that is, in fact, the area between those two curves, 1/3. Very, very simple. Now, sometimes, now this is going to work no matter what. As I mentioned, sometimes functions change, you know. Sometimes one function will be on top and on the bottom on one interval. On the other interval, you'll have the opposite function on top. Once again, what that'll mean is that you want to split this into two separate integrals. You want to take the interval, for instance, a function like this, a theoretical function like this. If this function is f of x, and this function is g of x, and we'll make it look almost like there's an actual axis here. Well, between a and b, it would be the integral a to b of, let's see, which one's on top? F of x minus g of x. But we also have to add that, b to c, to the integral b to c, wherein g of x is on top minus f of x. So that's the way that you'd tackle a problem like that. Finally, there is the concept of the dy integral. Everything we've taken so far has been, every integral that we've solved has been an integral with respect to x. Okay? Sometimes you can't really take an integral with respect to x. And a great example would be like finding areas of things that aren't necessarily functions. Let's look at this example. Y equals x minus 1. Okay, that's going to be a line. And the parabola y squared equals 2x plus 6. Alright? This presents a little bit of a challenge. So the first thing we need to do is we need to set the y's equal to each other. And what that means is that we have to solve the equations to find the points of intersection. Now, if you were to do that, in the interest of brevity, we'll skip ahead. The points of intersection, you're going to find that -1, -1, minus 1 is -2, -1 is going to be -2 plus 6 squared, the square root of that. You're going to get -1, -2, and 5, 4. You can plug in the y values and you'll make sure that that works. So we found the points of intersection. Let's go ahead and plot the curve. Well, the first thing you'll notice here is that we have the line 1, -1. It's going to go through there, and we know that -1 is going to be a point of intersection, and we know that 5 is going to be a point of intersection, and that would make this 4. So what we're going to be looking at here is this kind of parabola type thingy, and we're going to be figuring out this area in here. Well, the problem is that it's not going to be easy for us to make rectangles and solve these equations for those rectangles. Instead, what we're going to want to do is we're going to want to take horizontal rectangles. In general, whenever you're looking at a function that isn't, or whenever you're looking at the area between something that isn't necessarily a function, like y squared equals 2x plus 6, whenever you're looking at something like that, there's a pretty good chance that you're going to be using a dy integral. Trust me, it'll make things a lot easier. So what we're going to do, I'll show you why it's going to make things easier. Because instead of doing these rectangles, wherein we're going to have to solve a quadratic equation that's just going to be ugly, we can take dy integrals with respect to this line here, and it'll be so much easier. So the way that this is set up, to explain this, is we had that picture and we knew which one was on top. And we know, with respect to y, this is x, x, y, y. If we're taking an integral with respect to y, it's not going to be from -1 to 5. With respect to y, it's going to be from -2, the area is going to be from -2 to 4, because that's the y value. Alright, we don't need to take the square root now, so we can just plug in what y is. Well, we got x. What is x? X is y plus 1. That's easy. Y plus 1 minus, solve this for x. It's going to be y squared minus 6 over 2. If we're taking dy, if we're taking dx, we want the equation solved for y. If we take a dy, we want the equation solved for x. So we get y squared minus 6 over 2 is the same as y over 2, or y squared over 2 minus 3. And this is a dy integral. So we're integrating with respect to y, which makes sense because y is the variable. So what we do now, and just to remind you, we're doing this because we didn't want to integrate square root of x plus or minus square root of x minus 6. I mean, was that the equation? 2x plus 6. That would just be disgusting. So let's go ahead and let's integrate this. Between -2 and 4, y plus 1. Well, first, before we do that, before we integrate, let's go ahead and let's make this a little bit easier to work with. So we got negative y squared over 2 plus y, 1 plus 3 is 4, plus 4 dy. Now, we're going to be working up this time. going up, we can integrate this function very, very easily. You know all of the tricks. It's going to be the power rule here, so it's going to be negative y cubed over 3 times 2 is 6, plus y squared over 2, plus 4y between 4 and negative 2. And if we evaluate that, we'll get 1/6 times negative 64 plus 8 plus 16 minus 4/3 plus 2 minus 8, giving us a final answer of 18. So the area between those curves is 18. Pretty easy, actually. I think you'll find it's just the subtraction, the difference of integrals. It's an application of the law that we went over earlier. So that's, I think, all you need to know. So I have an exercise for you that you can try. It's going to give you some practice into this type of integral. So I want you to find the area between the curves. So you'll probably want to sketch this. You'll probably want to find the points of intersection, sketch it, figure out whether or not it's easier to solve for y or x, integrate with respect to that variable, and here are your functions. Y equals the square root of x, y equals half x, the line x over 2, and x equals 9. All right. Good luck, and I'll see you next time. Take care, y'all.